So in this mini lecture, we're going to talk about Newton's laws. So I'm sure that all of you have heard of Newton's three laws before, but let's just review them and maybe say them in a more sophisticated way based upon some of the terminology that we have from our last mini lecture, along with everything that we've talked about for vectors so far. One thing you definitely want to know about Newton's laws is, first and foremost, they're the basis of all those subfields of mechanics that we described in the previous lecture, but also they're empirically validated. And what that means is you can actually conduct experiments and take data that show that these are true. So Newton's first law is the law of inertia. When you hear inertia, you probably think back to somewhere in school where you learned that this means that bodies at rest tend to stay at rest. But let's actually put some formal definitions behind it. So the way that when you take a statics course, which is where I took actually that figure from, the statics text that's used both here at SAC along with everywhere across the country. For these fundamental engineering courses, everyone tends to use the same book. And what it says is that absent of a resultant force, a body's velocity will not change. Now, what do we mean by resultant force? Well, I encourage you to look around you and look at something that's not moving. And think about whether or not there are actually any forces acting upon that body. Like maybe I have my cup in front of me and I sit it on the desk. Well, since this cup is not moving, right, I might be tempted to say that there are no forces acting upon the body. However, since every object around you has mass, as we'll see on the next slide, that means that the actual Earth exerts a gravitational force that pulls it towards the center of the Earth. Therefore, since it is not moving and there is a force acting upon it, there must be some other force that's tending to basically counterbalance that push down. And in this case, it's the push up or the normal force that's being applied by the surface that this cup is sitting on. So what that means is that an object can be stationary and it can still have forces acting upon it. All that it means is that all of those forces, if we add them up, they add to zero. And that's exactly what the resultant force means. So that's an important thing to know, that the resultant force is just the sum of all forces acting upon a body. And since forces are vectors, we're going to have to add them using the laws of vector addition that we talked about in the last learning module. Newton's second law says that F is equal to ma. And if you notice, I'm bolding the F quantity and I'm bolding the A quantity. So both of those are going to be vector-based quantities. Remember that that's one way you can denote a vector is to actually write the variable name in boldface. So what does this actually say? Well, if there is a resultant force acting upon a body, so if the forces don't cancel each other out, then that body is going to accelerate, which is a fancy way, a vector way to say that it's changing its speed with a magnitude that's inversely proportional to its mass. So for a given load, a given resultant force acting on a body, the more mass that it has, the higher the tendency that it will not change its velocity. And that's why mass is often called kind of the inertial quantity of a body. So and you can see that if you actually solve for A, just get the A by itself on the right side of the equation, which you could get by dividing by 1 over m. And you see that the amount of acceleration you have, which is just the change in your speed, is going to be proportional to the force. So more push, more acceleration, and inversely proportional to the mass. So more mass, less acceleration. Here, I'm just saying that both F and A are vectors. So what do we have going on the right there? A times m. Well, that's an example of scalar multiplication of vectors that we talked about in the Engineering Math Part 2 module. Newton's final law is the law of action and reaction, and that just says that if two bodies exert contact forces on one another, they apply forces in equal and opposite directions. And if you think about it, just hold your two hands in front and push on your left hand with your right and your right hand on your left. If you think about the amount of push that your left hand is exerting on the right hand, assuming these two things aren't moving, then the amount of push that your right hand is exerting on the left hand is equal and opposite in that case. So in addition to the Newton's three laws that you traditionally call Newton's law, just note that he is also responsible with describing the gravitational phenomenon around us. And what that says is that if two bodies have mass, they're going to tend to attract one another. Now, you might say, well, I'm sitting in a room with a bunch of objects around me that have mass. Why aren't we attracting each other? And it's because Newton's gravitational forces are actually a very weak force, as we'll see here in a minute. But the formal formula for Newton's law of gravity says that the gravitational force between two objects is proportional to the mass of both and inversely proportional to the square of the distance really between their centers of gravity. But you don't need to worry about that for now. Just think about it as the physical distance separating the two things. So G here is your constant of proportionality. And you might look at this symbol and be like, well, what does he mean by the R with the hat over it? So since that R is bolded, that gives you a hint that it's a vector. Remember that forces are vectors, so we need to describe their direction somehow. And since this is just a scalar, we'll describe the direction by scaling that number by a vector. And this hat just means that this vector has no length. It's what's known as a unit vector. So the entire magnitude of the vector is coming from the scaling quantity out in front. And this vector r is just directed along a straight line between the centers of gravities of each of the two objects. So you can see here that g, the gravitational proportionality constant in this equation, is incredibly small. And that's why you're only going to see evidence of gravity when one of the two objects that's acting upon one another is very, very large, like in the case of planetary motion or your attraction to the Earth. Now, for those of you, I know there's at least a couple of you that are taking electrodynamics now or the second physics course, and you've probably seen a formula that looks a lot like this. If you just swapped in the G for K and you swapped out the M's for Q's, this looks a lot like Coulomb's law that describes how particles that have charge tend to attract or repel one another. The one thing you should know is that Coulomb's law, that constant of proportionality, is much, much, much larger. So electrical phenomena actually exert electrostatic forces, which just means charged particles that are stationary. They act upon each other in a much stronger fashion than gravitational forces. However, you don't see a lot of evidence of electrostatic forces around you because by and large, most things are neutral. They don't have a net charge. And so that quantity in the case of electrostatic forces isn't mass, which everything has, and you can't kind of cancel it out. It's charge. And remember that charge from a physical perspective, there's two poles of it. There's plus and minus. So in the aggregate, they can cancel each other out. So let's talk a little about weight. I'm sure that all of us have heard the term of weight beforehand. So if you think about it, if I just substitute, this is the same equation that I had on the last slide. If I just substitute in the one of the two masses for the mass of the Earth, and this is a mass of an object, and I were to say that this is, by definition, if Newton's law of gravitation is true, this has to be the force that the mass of the object and the mass of the Earth exert on one another. So if I equate that to Newton's third law then, so if you notice here, all that I'm doing is taking the expression that I have above and setting it equal to m times a, I can actually cancel the small mass term in this case. And what that will tell me is if I'm interested in understanding how much the force that the Earth exerts on any object accelerates it, that object is represented by the mass m, that acceleration that is due to the gravitational force is going to be equal to this. Now think about what all these numbers actually mean. Well, the gravitational constant g, that's just a number. And the me, right, that's just the mass of the Earth. That's just a number. And this r squared term is going to just be the distance between the center of the Earth and any object for which we're trying to calculate the acceleration due to gravity. And even though this number varies depending upon where you're at on the Earth and how far you are above sea level, by and large, it's got two components to it. It's got the radius of the Earth, which is a really, really big number, and it's got whatever little marginal elevation you have from sea level in this case. So you can actually approximate this as relatively constant. And that's why people will often say that when you discuss the actual acceleration due to gravity, that you can approximate it by some constant number. And here we see 9.8 meters per second squared is often a formulation that you will see for the acceleration due to gravity. And what that will allow you to do is to compute the weight of an object relatively easily by just taking its mass and multiplying by the acceleration due to gravity. So if you got anything out of that, just know that Newton's law of gravitation, you can use it along with Newton's third law to actually define what the weight of an object looks like. And you can see that weight is always going to be directed in the same direction of this constant acceleration due to gravity towards the center of the Earth, and it's going to be proportional to the mass of an object. So let's actually look at another example problem involving this wheel on the rail. So assume that you have a concentrated force exerted by the rail on the wheel. So this is that white force vector that you see pushing up, and assume that it is 500 pounds. So let's describe the force exerted by the wheel on the rail and justify your answer with the physical law. So think about that before you go any further. What this description says is that there's a 500-pound force exerted by the rail on the wheel. So the rail is pushing the wheel up by 500 pounds. So what can you say about the force that the wheel exerts on the rail? Well, by Newton's third law, right, go back and look at it if you don't remember. That's the law of action and reaction. If the rail is pushing the wheel up by 500 pounds, then the wheel must be pushing the rail down by 500 pounds. So you can actually write an expression for the force that the wheel exerts on the rail just by knowing the force that the rail exerts on the wheel, since it's a Newton's kind of reaction law pair. For the second bullet point here, assuming that the wheel is stationary, are any other forces acting on it? Justify your answer? Well, think about that. We know that the rail is exerting a force up on the wheel. If there were no other forces acting upon it, then that wheel, according to Newton's second law, would actually accelerate in the upward direction. But if this thing is just sitting stationary here, we know that there must be no resultant force acting upon it. So if the rail is pushing the wheel with 500 pounds up, there must be some force that's pushing actually the wheel down. And by and large, likely just a simplification here, that's likely exclusively to be nothing more than the weight of the wheel. And the weight of the wheel, as we discussed here, would be directed towards the actual center of the Earth. So the key thing that you need to note there is by Newton's second law, if there's a force exerting on this wheel and it's not moving, then there must be some other force that's tending to cancel that force out. And that's really the answer to that part. And most likely the only other force acting upon it in a stationary configuration would be, I mean, there are some contact forces at the point that you have the axle connected, but the main force that is exerted on that wheel is just its weight going in the downward direction. So hopefully that was a bit of a review for a lot of you. I understand that was the first time you're seeing a lot of these concepts. A lot of those words are kind of confusing, but don't worry too much about it. Just let it sink in. Make some notes and try to get the best that you can out of it. And you'll get an opportunity in the homework next week to actually go back and review and make sure that you kind of get the basics that you need in order to prepare you to take your physics classes if you haven't taken them yet, and also to take your introductory mechanical engineering courses that all of you will have to take.